Hello, everyone. Welcome to today's webinar on AI-enabled asset and energy management. I'm Neeraj Nair, Principal Consultant here at FutureBridge from the Energy Practice. So before we begin, a quick introduction to who we are as FutureBridge. We are a techno-commercial consulting and advisory company, and we track and advise the future of industries from a 1 to 25 years perspective. This means that we deal with technologies and innovations, market opportunities, business models, and how the competition is behaving, and the regulations which are involving in the given landscape. So this is our work for a variety of clients across various industries. And here today we are focusing on the energy practice and the implications of AI in the times to come, especially in the electricity business. Thank you once again to each one of you for joining in. And at the outset, I would like to mention that this over the course of next 30 minutes, our discussions are divided into two broad elements. One is the AI-enabled asset management, where we look at the need for AI in the first place for managing the assets across the electricity value chain, and also some of the elements of AI which makes it an interesting case for consumption by the energy industry as a whole. And the second part is where we look at the specific problem statements in energy management, which is best suited to be addressed by AI. And it is imperative that all of us stakeholders take cognizance of the wonders AI can do for the increasing complex systems that we are building of late, given the dynamic nature of the requirements itself, be it data centers or electric vehicles, and on the other hand, the great amount of decarbonization which is expected, which is required, and it is being fulfilled by a host of renewable energy sources which are intermittent in nature and spread across discrete geographies across the world. So let's dive in to the first module, which is AI-enabled asset management. And here is an overview of what all entails, both in present times, the best practices in the industry, and what demands are being placed on these existing systems or practices that necessitate the implementation of AI-enabled solutions. So be it, for instance, asset reliability, the manual means of working on the aspects of root cause analysis and so on. These systems are good when the systems are fairly simple to deal with, but with the discrete nature or the democratic nature of energy generation and as well as the consumption, there are now an order of dimension higher, or if not more, number of failure points and a corresponding volume of data which needs to be processed to enable the decision making, or be the asset operation. So there are very telltale signs of failure which get missed out by human operators. We need this on a dynamic optimized model in a real-time basis for effective decision making and improving the overall efficiency of the assets, which is the requirement of the modern day networks. It could even be in planning, where traditionally we have relied on historical data to build systems for the future, but the situation is rapidly evolving as we speak. So these plannings, which take typically a horizon of, let's say, the transmission business, 5 to 10 years of planning or advanced planning are involved. But by the time we reach maybe 2 or 3 years down the planning circuit, things have already changed quite dramatically because of the many moving pieces which are spread across a vast area of geography, or in any given area of geography. So this means that we hear the voice of the assets as one cogent system rather than a static entity. It's more of a living organism which is evolving and fluid in nature, and this means that there are some time sensitivities attached to each decision we make, and it cannot be a preset course which can be dealt with based on historical data. So all the more important that it's not a human-only plan, which is then which can then address the evolving situation, but it has to be delving into multiple operational areas with an immense amount of data points, all at any given point in time, which is humanly just simply impossible to bring the scale of perfection or the repetition which is necessary across the various nodes in the value chain. Or it can be even in terms of safety, where there are some early advantages which are being offered by AI, especially the core strength of image processing and natural language processing, the models which we are quite familiar in today's times. So the image-based assessments could benefit a great deal from the capabilities of AI, and the human and asset safety which it then brings along adds a great deal of value in today's complex times. It can also be field services which have traditionally relied on a routine of work order creation and dispatching those solutions, but with improved services which are expected by the consumers, and the consumers themselves are varied in nature, and with automated responses to many events in the network, be it the price signals or the frequency signals. All of that has to be addressed in a real-time basis to get an improved return on investments, or even to maintain the return on investments which are typically expected of these systems that we are familiar with. So if we look at the elements of AI, it's not a monolithic actor, but rather it has various levels to it. Machine learning, for instance, is just the very beginning, which has been in place for 10 to 15 years already, but now it is moving beyond to address a discrete data universes all at one go. So if we take the case of generation assets, there could be the power plant fleet information along with the price signals, the weather, the various events that in which the any power plant finds itself in. All of these data has to be processed real time simultaneously to bring it all together to make an informed decision. So the key is in leveraging all of these data sets together and then align it with the human values which we would like to see in these systems as they operate. So it has to be aligned well with the experience or the expectations, let's say, of an experienced operator, and also the regulations and the end consumers, which expect a certain level of grid quality and responsiveness to each of the actions which are brought in by the operator across the value chain, be it the generation assets or even the T&D operators, or even the load management services of the distribution utility at the tail end of the system. So having said that, the elements of AI has to be judiciously implemented across the problem statements which make sense or which are expected to benefit out of the capabilities of AI, starting with some of the first movers like uh, asset management or visual inspection of T&D systems and so on, which is quite difficult or time intensive to be done manually. And when it comes to a whole lot of sensors and actuators which are now commonplace in the network, which generates millions, if not billions, of data points, it is all the more essential that these are organically looked at as one cohesive unit, using the capabilities of AI to deliver the results which we have come to expect as a default in any case of an operative scenario in the electricity business. So what does it bring in? So what we are seeing is we are expecting redefined efficiencies in the new normal, which is evolving. So assets are already decentralized, and there is a changing operational requirements, be it from the regulatory perspective or the safety compliance. The expectations are immense, and to ensure that the ease of operation continues, we cannot just impose it all on the human personnel or the human resources which are involved, but rather it needs a more automated and effective solution, which can only be enabled by something as powerful as AI systems, which can then deal with the emerging challenges which we see now in the grid. Or it could be the renewable energy requirements of for decarbonization. While it is has become quite cost efficient to implement new renewable energy systems. But when it comes to traceability and looking at the scope 3 emissions, which are way beyond the typical operating boundaries of a power plant, then the complexity increases by a whole new dimension. The processes are expected to be executed in a place where the data points have increased exponentially or by many orders of magnitude. Add on to it the importance of maintaining all the legacy infrastructures, which again has multiple vintages. All of them might have their own systems of operation, and understanding it all together in one a universal system is a task on its own. Now, this also is a place where AI can add a great deal of benefit without manual intervention for each systems, a system of systems which has evolved over a period of time. This can be managed with a great deal of reliability and efficiency using AI. So that's the value proposition: redefined efficiencies, aggregating efficiency gains while at the same time ensuring that there is an ease of operation and achieving sustainability targets and the expectations of efficiency, which are again expected everywhere across the stakeholders, dealing with highly granular data with a great deal of interdependencies. Now, what does it mean for a stakeholder if we are to adopt some of these AI solutions? And these are important, especially if you are a decision maker in the value chain. Now, though it appears quite simple, uh, human interaction or identifying the problem statements, that is one of the most important challenges to be addressed in today's time. We identify the key pain points by speaking to a vast cross section of consumers, be it operators or the system planners, for instance. These need to be brought in together along with the emerging regulations, and then identify these business needs and use cases in a realistic manner, maybe even conduct workshops and industry forums to voice out these issues, and first make a list of all these problem statements which could practically stand to benefit from the implementation of AI. The next important stage is that we prioritize them meticulously. Not all problems can find a solution in AI-enabled systems. There are some first movers. One of the easiest examples to quote here is visual inspection, which is quite advanced using AI processing capabilities, and the volume of data is also significant, which warrants that an AI system be enabled. So we judge each of these problem statements in a individual manner and rank them in a priority order, so that the systems are then built in place, which adds meaningful value in a cost effective manner. So that's the second order of activity. Apart from the human interactions, the early signals where the consumers had headed, we prioritize the areas of activities which can benefit from AI, and then something like the use cases, which could be surveillance, which could be human-machine interfaces for operators to work on. So these are the priority areas we build in. And then the third stage is that we ensure that there is sufficient data which is available to power these systems. It all ultimately hinges on the volume, the quality, and how well we have maintained that data, or be it historical or be it the elements of data which comes from the various sensors. They need to be in place and well aligned to work with the AI models which we then bring on. So once you cross these three checks, then we are in a position to really look at how we go about implementing these AI solutions for asset and energy management. So when we speak of the implementation phase, it starts with data always: collection, cleaning, transformation, reduction, and then finally validation of the data sources. So once we have done that, it's a typical IT workflow, but albeit with certain differences. The pilot phase is one of the most crucial amongst these, where we select the model which can be used for the particular problem statement at hand, and look at what kind of training possibilities exist, again dependent on data, and more importantly, validate some of these solutions which are prescribed on a real-time basis by the AI models. And then we deploy it on a pilot basis to see real reactions from the system, and also the human interaction with that then happens along with it. Once this is through and we are fairly convinced that this is a viable solution, it's deployment ready, then comes the decisions on investment, what kind of phasing of investments are required. It cannot all be done in one go. And always the objectives are not clear right from the beginning. So we have to start investing at one phase to a limited set of objectives, and then also be mindful of the fact that in the future there could be more elements that can be added on, and it has to be quite flexible and modular in nature to ensure that all these investments can flow in seamlessly with the right degree of flexibility, and while still maintaining the ability to deliver the ultimate objective that is set within the organization. So starting with data sufficiency, and the pilot confidence building, and then finally into making investment decisions. That's a typical flow process of an AI adoption in any given node in the value chain for the energy business. So how are energy players finally benefiting out of all these? Some tangible results. So it can prevent failures and downtimes well ahead of time without the need for a reactive basis. And it can improve the GHG emissions reduction, the OPEX, which is spent typically on the operations, and so on. So this is addressing both reliability and asset operation. Now, what it brings with it is the challenge of the ability to solve hundreds of problem statements at one go, deploying thousands, if not millions, of different models for the vast spectrum of equipment which goes on to make the electricity network work. The granularity of the requirements, that's another aspect we need to be mindful of as stakeholders in this, where we bring in a lot of asset integration along with the sensors and enablers or feedback mechanisms which go with it. And the ultimate success is in monitoring all of these pieces of information in a cogent manner, where multiple models, a system operates to deliver the results what we are expecting, and there are instances of 15 to 30% of decrease in energy costs purely by managing our system of systems better, and upwards of 25% reduction in GHG emissions, which are some of the broad objectives of any operator in the energy sector. Now, we move on to the next module, which is AI-enabled energy management. So again, we begin from the same point where there is an explosion of data, renewables which are discrete and variable in time, and this is particularly to in the electricity segment, where uh, both the supply side is dynamic in nature with the variable renewable energy and discrete at the same time, and on the demand side as well. The new age consumers, be it the EV charging or be it the huge data centers with extremely flexible load. It has a load factor of near 100% during the training phase, and then it suddenly drops to maybe 30% at the next stages of its beyond the training phase, be it the inference phase, and so on. So what it brings is variability across the different nodes from start to finish. And there is a collective ambition which goes along with this new paradigm, is that a self-healing kind of adaptive network is what is the expectation for a stable operation of the energy system as we know it. And that brings us to the three V's, which is data volume, data velocity, and the data variety which is involved. All these put together adds a great deal of complexity or to the solutions which are required, and that's where AI is a necessity now more than ever to deal with these emerging situations of data overload. So traditional systems just cannot fulfill all the quality and qualitative and quantitative requirements which are placed on by each of our stakeholders in the ecosystem. So if we break it down to what could be the places of adoption, the present and the future, if we look at across the various nodes of the electricity value chain. On the generation side, it could be the predictive maintenance to begin with, be it even for conventional power plants, the fossil fuel power plants, which requires a great deal of flexibility given the variable nature of all the host of the fleet of renewable energies which is getting added on to the network. So ultimately, the future would rely on autonomous plant control, which can be AI native energy management systems, which does its own decision making in real time to manage these fluctuations in the network. T&D can benefit a great deal from dynamic line rating or voltage management, which again calls for multitudes of data, visual tools for implementing all these solutions, and also some first movers could be the visual inspection tools which we mentioned earlier, and ultimately maturing into a system where the grids are self-healing in a real-time topology optimization manner. Trading is another area which could benefit a great deal. Agentic AIs would ultimately act as those traders through smart contracts. Implementation of smart contracts could become a reality in a 24/7 automated settlement manner. On the distribution side, as we move from more and more into secondary and tertiary forms of energy, moving away from the primary fuels, it is extremely important that the products which cater to these type of consumers are diverse and flexible and agile as we speak. And there could be cases of prosumers as well who feeds back into the grid, which adds another set of issues and challenges which can be effectively addressed by AI systems, which then brings in hundreds of megawatts of gigawatt scale VPP integration, and then we ensure that there is a near time settlement in the near real time settlement of markets, which is adaptive to the situation at hand on a minute by minute basis in the electricity network. So here is an example where we look at a conventional fossil power plant where the challenges are that it has to adapt to the grid. There is a dynamic nature of consumers with various price signals. And on the operator side, there are various experience levels or experience areas which needs to be handled simultaneously. Be it the physics of it all, the pressure, temperature, and the fuel firing rates. And then a typical operator looks at with the case histories and the system snapshots from earlier times to really make decisions in real time. All those experience has to be brought in together, which is today done by experienced people who are retiring more and as we speak. And then there is the discrete nature of democratic renewable energy systems which are coming up, which means that we have to pass on these experiences across multiple points in the grid, which is simply a difficult uh, human resource staffing situation, or be it the forecasts which are required to be done on a preemptive basis. All of these together can be addressed by an AI-based approach where we assimilate the history or the repository of knowledge, enable it with digital twins to evaluate on a real-time basis, and then reinforce all these information with human feedback to make decisions which are in line with the expectations of the humans in a time bound and pressure in a high pressure situation where a lot of data points come together to make informed decisions or for the greater good of the network and the system at large. Uh, eh, if we look at the transmission side of things, it would be the multivariable nature of these problems. Let's take the case situation of US, where there is an increasing demand for data centers. Uh, Almost 50% of the new energy demand by 2050 could be coming from data centers. That's one estimate. And add to it the complexity that almost 70% of the assets are close to, 25-year plus, many of them close to retirement. And this further exacerbates the, situation at hand, wherein there is a 3 to 4 times scale up of renewables which are required to meet the green energy commitments or the net zero ambitions by 2035. And on the consumer side, there is a dramatic increase in the requirement of energy. The modern data centers or the process compute power which consumes almost 8 times the power of a traditional system. These kind of massive loads which are coming in into the system, it's a highly challenging situation like we have never seen before. So there is a surge in demand along with an aging infrastructure and the complexity that renewable energy brings in. These kind of multi-dimensional problems is something which is being experienced in transmission and distribution networks, and all the more important that AI-based solutions can really add value to these kind of energy emerging scenarios, which account for the three V's again: the great volume of data, the variability in each of these data points, and the speed at which, the velocity at which it is hitting at any given point in time. So, so what's the essence of it all? Where do we go next from here? So what we see is that it will move on from today's reactive nature of things, where it's a break and fix model, to a predictive means, wherein we see problems before they arise. That there is a dramatic shift from a calendar-based repair and maintenance schedule to a condition-based schedule. So that there could be a delay in investment which can consciously make, and at the same time there could be situations where we avoid the downtimes altogether by taking preemptive measures to address these situations of the grid on a real-time assessment of the health conditions. Digital twins will then be adopted maybe in a 2 to 4 year time horizon 2, and that could be also implying that there is a massive mobilization of edge systems, which is again powered by AI, and this ensures that many of the settlements would be done at the point of action rather than carrying it all the way back to the centralized networks, which is anyway not the case. And then ensure that these physics models are delivered at the site of execution, be it the DERMS platform for EV or the solar and battery systems, which many of the prosumers use, and all of these working in a predictive manner. So there's a great deal of work for the utilities where they have to identify these systems, vet it, attune it to the regulations, and on the OEM side, there has to be the development of the protocols, the industry standards, and development of these effective models, which can be then enabled into the AI-based autonomous operation in the Horizon 3. So ultimately, where we see this industry going is millisecond decisions, taken in a very confident manner, aligning with the expectations of the regulators and the consumers. A self-healing topology wherein there is minimal human intervention is needed, which means that the onus on the human element is that we ensure that these processes are vetted correctly, and we develop protocols for the accountability. Ultimately, rests with the people signing it off, and how that can be well managed to ensure that there is a great deal of trust which the users have on these systems, which deliver the results in the way it is expected uh, at any given point in time. So overall, a very exciting phase of growth for the electricity industry. We need to make careful, measured steps, ensuring that we prioritize all the problem statements, bring all the stakeholders together, and embrace AI in a way that it is least disruptive uh, to the ecosystem, but at the same time, uh, accelerating the journey to the next stage, wherein there is an autonomous and highly efficient system at work, which helps us ensure that we meet all the goals of decarbonization, and at the same time delivering value to the customers, the end consumers, and ensuring that all of these is done in a cost-effective manner for all the operators in the ecosystem. So that brings us to the end of this conversation. It was a pleasure speaking to you on this very exciting topic. Stay tuned for our next webinar on an even more interesting topics very soon. Thank you so much once again. Thank you from FutureBridge.